Right. So the bit that I'm going to present, it's moving more to the surface. And let's talk a bit some of the additional libraries that we have found. And one of them is from this consortium or institute. It's the Open Energy Modeling Framework. And they have been investing in quite a few libraries and developing quite a few libraries that are completely open source. And the one that I'm interested to discuss and show you, it's the one called TestPy. So TestPy stands for Thermal Engineering Systems in Python. And it's a simulation, it's pretty much a simulator where we can mimic the whole network at surface with the different components from pumps, condensers, turbines, and so many other equipment at surface. And we can also model what are the type of fluids that are used across the different systems. Heat exchangers, for example, can be used as well. What I was thinking about this particular library is that we could estimate, if we could estimate how much is the outflow or how much is the water, the hot water and the steam production from the system, then we can estimate also with the library how much is the instantaneous power supply potential. So the library itself has quite a few examples, and it's if you see here, they have a very detailed explanation of how the library works and the different elements that they have, the network components, connections, and so on, and the fluid properties as well. And they have in GitHub, if you go to the OEMOF, Open Energy Modeling Framework, and they have a few other libraries. The one that we're going to use is this one called TestPy. And inside they have also, well, they have some tutorials, but actually if let me get out, because they have many more examples. If I got here into the OEMOF examples, and they have the examples from different libraries. And here you have quite a few examples. So before I start to open one example, I'm going to attempt to build one example from scratch. And this looks very similar to what it would look into a setup of a surface facilities from an oil field, where you have your separator, you have your pipelines, and you have multiple separators, and you have a tank. Well, in this case, we have so many other components, and what we are trying to estimate is how much is heat generation in the system, how much is the energy generation in the system, and so on. As Igor mentioned, there are quite a few types of geothermal power plants. So the first one is a dry steam, where you have steam production all up to the surface, and there is a turbine that is generating electricity, and subsequently, once this is of course an oversimplification of the system. There are so many other components going around, and but this is what I want to show you first, and then we will go to a more complex example. But then once you have a steam production, you can inject pretty much the water, which is the cold water, into a system. So if you think about it, this is a source, and this is a turbine element or component, and then we have the sink. And the turbine itself would have a generation capacity based on how much steam it's being injected into the system. There are some others. Igor mentioned the binary cycle power plant, where you have it's similar to the one we saw before, but there is a work fluid in the middle, and there is an exchange. The steam, it's actually driven or generated by this working fluid, and which is a bit more efficient in terms of in comparison to the water. So that working fluid is recycling the system. And then the other one is where you have a flash, you have hot water, and eventually you have pretty much a separator at surface, and you take the water out of the system, and I'm simplifying the example, but and then you get the steam into the turbine. So sort of a high level definitions. So I'm going to create a simple plant example. As I mentioned, the library, it's called test.py. So first of all, there are three main type of elements that we have to use in the library. The first one is components, the second one is connections, and the third one is a network. And the network is the one that encompasses everything. So let's start with components. So from test.py, not test.py, but ESPy, dot components. Let's import. And there are quite a few things that, let's import. I want to import in this one three things. I'm going to make it very simple. And I'm not quite sure if this is the right modeling approach, but we will see a more appropriate one at the end, where I will show you a full geothermal plant setup. So let's import a turbine and also a source and a sink. So which are the three elements the basic elements that we need in the system. Again, there might be other elements that we need, and there are obviously efficiencies that we're not taking into account. I'm taking into account that we're fully taking the steam into the turbine, and then we're generating electricity. Of course, there are other things that we need to power, like pumps and so many other elements at surface or equipment at surface. So the other thing that we need here, it's, as I mentioned, the connections. The way this works is, I'm going to import connections. I'm going to import connection, and I'm going to import the bus, which is actually for the power generation. That's where we need to, let's say, plug the component for the power generation. And the last thing that we need is to define the network. So from networks, let's import network. So I'm going to create my network. Let's call it NW. I'm going to use this network. I'm going to instantiate from this network object. And the things that I need to provide here are the fluids. And in this case, we're going to assume that this is water. I'm not quite sure, but the way it's defined, the water in this example, it's by cubic and water. You can try at some point to define a different way, but I think this is related to the reading of the properties inside the other libraries, like the ones that Igor mentioned. The units of this example, it's going to be in bar, pressure. The temperature units, which is another thing that's nice on the library. It can switch around units in a flexible way. And in this case, we're going to specify also specific heat units, which is a kilojoule per kilogram. Let's see if that works just as it is. Oh, kilogram. Okay. oh, sorry, kilojoule kilogram. There we go. Now let's start to define the different components. The components that we have, let's use a high pressure turbine. So we're going to instantiate the turbine, and let's put a name to this component. And in this case, this is a high pressure turbine. And then we can use steam, and the steam is going to be my source. And I'm just going to call it steam. It's just a label. And you will see later on where we're going to set up what is that particular sort of fluid. And there is a cold water injection, and that is going to be my sink. And this is a cold water sink. The next thing that we need to establish is a connection. So as I showed you in this example, I want to just connect my source into a turbine, and then the turbine into a sink. And I can set it up in the following way. So that's a steam to high pressure turbine. That's just a name. And I'm going to establish a connection, instantiating this object connection. And so the steam, this steam will go out into the high pressure turbine. And the other component that we need is a high pressure turbine into the cold water injection. And this is connection again. And then here we have the high pressure turbine output. And this we need to label this out one, in one, because there are some components like a condenser that could have a couple of outputs or a couple of inputs. So we need to make sure that we label them properly. And then we have a cold water injection and the input one. So let's see if that works. So that's already my connection defined. And now all these are kind of independent systems or independent elements. We have the connections, we have the components, and we need to add it into the network. So the way it works is we have this object NW, which is a network. And I'm going to add the connections. And my connections are the steam to HPT and my HPT to CWI. Okay. Now, the other thing that we need to have is a bus component, which is the actual energy generator. So that's a power component. I'm going to call it PWR. And I'm going to instantiate this object bus. And I'm going to call it power. And let's add the component that actually generates the electricity here. So I'm going to add the components, different components that generate electricity, and we have the way to provide it is through a dictionary in Python. So in that dictionary, I'm going to provide the name of a component, and I think that should be it. So that's a component that is actually generating the electricity. And now, as I added the connections to the network, I need to add the buses. And in this case, we have the power. And the buses we may have elements that are using electricity, using power, and some other elements that are consuming power. So there we go. We run that bit also. And just so before we run the network, and the way to run the network, it's very simple. I can go into network and then solve the network, and let's call the solve the solution as designed, but that's going to give me an error because I need to provide some additional information. The information that I need to provide is, for instance, for the high pressure turbine, I need to set some attributes. And the attribute that I need to specify in this case is the efficiency. As Igor mentioned, the efficiency of the system is probably around 90%. So let's assume that this is a 0.9. Usually higher efficiencies, as in oil and gas, leads to higher investment, operational investment, or also capital investment in terms of redundancy of equipments. And in terms of turbines, if you want to have a high uptime, you may have to have a redundancy in terms of turbines. So for this type of projects, that might be quite difficult to justify. But if the electricity price is high, then you can probably justify having redundancy and keeping let's say the uptime close to 95 or 99% even. But let's assume that this is 90%. And then we need to specify the steam to HPT. We need to set a few attributes. And this is where it gets quite tricky. So I need to specify what is the mass, the instantaneous mass of steam that it's going into a system. And this is in kilograms per second. And I'm going to put 10 kilograms per second, which is equivalent to 5,000 barrels of water per day. If we have, let's assume one well. I'm going to assume that the temperature of a system, it's around 300 with an output pressure of 100 bar. So the fluid, it's going to be defined as water, and I believe it's going to be defined as the water, and we have to define all the components. So in this case, it's just water and, at 100%. And obviously the conditions will be flashed at these particular conditions, that water. So the other one that we need to specify, it's HPT2 or the turbine to the cold water injection. And we can set the attribute of what is the outlet pressure for this one. So if we set those attributes, oops, what's happening there? Oh, this is a dictionary, so I need to put 2 points here, boom, boom. There we go. So we have the solution, the system it's from. There are a few iterations there. And we can also go into the print of the results. I think this is a method. And what we have here, oh, that's not good. I'm having a negative value here. Let me see if I'm missing a couple of things around. One thing that I didn't put, I wasn't quite sure what this is. They have this char -1. That's probably the one that is causing troubles. Yeah, so that's just reporting the power generation in a positive units. So that's it. And I think you will realize that now we have the total power output, and it's around 70 kilojoules per second. 70,000, which is around 70 megawatts. So that's one simple example. And of course, what's the potential of doing this in Python? We can put an optimizer on top. We can start to play with these outputs very quickly. I can probably set a for loop I'm going to make a risk of doing that. So, but I can, I don't know if we can do something like this for, let's establish some outlets pressures, or actually let's play with the temperature, the inlet temperature. I'm not quite sure if that would be something that we could do. Let's say we have a separate process that it's that where we can modify the temperature of the steam. So let's go from 250, 300, 350, 400, and I can look to these temperatures. I believe that will be steam. And from temp in temperature steams, I'm going to override this property. Just this property. And hopefully I should be able to run again the whole design. So I should be able to run again and print again the results. See if that works. Okay, there we go. We have it, the 4 solutions. And one thing that I'm still trying to figure out is how to extract this number from the print results. So I can do some more nice stuff like plotting the outlet power based on any particular input. So the other example that I wanted to show you was this one. That's actually reported on the examples of the library. And in this case, they have very similar to the scenario that Igor was talking about, where you have a high pressure turbine feeding into a mid pressure turbine and finally into a low pressure turbine. So you have those 3 levels of, and you have also some elements, for instance, let me double check, but let me go straight to the output. If you see the power generation, there are quite a few other components here. We have a high pressure turbine, mid and low, and then we have a feed water pumps. So for the feed water pumps, the system is actually using some power for those pumps, as you can imagine, while for the turbines, we are generating electricity out of it. So the total power supply, it's actually estimated based on the total electricity of the system. And this is very similar to the example that I was showing before. So we have a network, we have components, and we have a few other things. We have a heat exchanger, we have the superheater, cycle cluster, pumps, condensers, and so on. Connections are the same. It's a connection and the bus. And what they have here, it's as you can see, when in this example, when there are 1, 2, 3 turbines with different names and different labels, and then in the connection you have cooling water and a source and sink of cooling water. I think that this is for the condenser. This is a separate process, which is very interesting because they have, this is actually a more complex example where they have this cycle cluster that it's supplying some fluid into the system, but this cooling water, it's a separate process that is working on the condenser. And then you have the connections. Exactly the same as the example that I was showing you before. And when you have a cycle closer to the high pressure turbine to the splitter 1. And this is what I mentioned, where that you have in some cases, for instance, on this one, you have an input 2. So this FWH1, which is a condenser, has 2 inputs. So at some point, FW H1 will have another input somewhere. I'm not quite sure where. Okay. I guess somewhere around here. There you go. Input 1, input 2. And then you have the buses, which is for the power generation. And then you have the high pressure turbine, mid pressure turbine, and low pressure turbine, plus the pumps, which actually are using energy instead of generating energy. Then you have efficiencies of all the different elements in the system. And finally, you have the fluid that is using in the cycle cluster, similar to the example that I was showing. So if I run this example, this is just setting up. And actually, let me just set up the example. In this case, they are using a class here, and a class to specify all the properties of a plant. So I can actually create multiple instances of a plant. So let's say this is my plant. My power plant is equal to that power plant object. And then I can straight away solve the network. If you see what are the objects that we have here, we have network, power, heat. So I can specify network, and I can solve the design of this network. And that's it. So then I can go into my power plant, and inside the network, exactly as the other example, I can print the results. And let's see how much, as I mentioned before, that's much higher output than the previous example. In this case, I'm not quite sure how feasible it is, but I guess it is. We're talking about 200 kilograms per second. That's that is about 100,000 barrels of water, or equivalent in steam. So it's quite large amount of fluid going through the plant per day, and it's a much larger plant. This is a 250 megawatts plant, which is very big compared to one of two examples that we were showing before. So again, that's it's very simple, and I think obviously driving the tool, and you can play with the design, and especially at very early stages of a project, this can be something that could be used to assess the potential of a project. So that's it from this particular library that I wanted to show you. Do you have any questions?